So first, I'm gonna start the talk by a little apologies to make a clickbait title for my talk. But since random is not really the most fascinating things to speak about, random generator, I try to make it a little bit fun at least. And we will see. So let's start a little bit about presenting myself. So my name is Adrien Devresse. Not that who I am is really relevant, but at least you're gonna understand more like how the talk is structured and why I structure it this way. So I have around 15 years of experience in C++. I have a background mainly in HPC, distributed system, embedded system, and storage. I work at CERN. I guess I don't need to present CERN. In the Human Brain Project, which is a project that tries to simulate human brain on supercomputer. I work for some startup. I work for Woven by Toyota, like some other colleagues that are here around. And recently I changed and I'm onboarding for the Square Kilometer Array, which is a radio astronomy project. Disclaimer a little bit about this talk. This talk is about like practical usage of random generator. If you look something about like mathematical properties of the random generator, I'm not a mathematician, so you're gonna be a little bit disappointed. But it's centered on the C++ even random, like pure, not any other library that come left and right. Please, especially if someone see that on YouTube, don't use that or anything that I present on any cryptographic application. Like that's a very bad idea. That's not what you do with this type of random generator. And it's focused on scientific computing mainly. You will understand why. So let's try it by a little story first. So this is the story of Bob. And Bob is your typical PhD student that you get in any university or school. Bob is interested of two things mainly. One is procrastinating, like me when I did this slide for this talk, because it's what PhD students do. And the second one is he wants to write his nice scientific simulator to finish his PhD, because after all he's a PhD student, so it's what you're supposed to do. And for this talk we are going to focus on the second one. A few things about scientific computing, because Bob is currently doing scientific computing. He's writing a scientific simulator on his aim in order to write it first to do it in C++, because most scientific simulators are in C++. When they are not, they tend to be in Python with C++ wrapped behind, so you're in C++ anyway, with a bit of fortran left and right. Most of them need to be fast, so that's the reason why you use C++. Most of them rely on random number generator quite heavily. If you do neuroscience, like I was doing in the Human Brain Project, spiking neuron, you need a lot of random number. If you do physics, you need a lot of random number for Monte Carlo simulation, this kind of stuff. If you do biology, reaction diffusion, all of that, you still have random number heavily behind it. And you better have correct random number. Like this is not your average random number that you do for 5 tests on generating few characters for your unit test. Like if you have bad properties of your random number for this kind of application, your scientific result can be broken, bad, or have correlation that are not due to what you look for, but due to bad usage of your random generator. Most of it, they are parallel programs. Like you want them to be multi-threaded, or most of them are also MPI programs. So, easy part. Let's get back to Bob. So Bob needs to choose between the two random API that we do have in C++. So you have a choice for the C world, and you have a choice for the C++ world. Bob probably looks like everybody when you want to learn something another day. So he looks on YouTube, because nobody looks to documentation anymore. And he understood pretty quickly that the old C random generator was not the future, especially not if you want to respect what I presented before. So let's get to the harder part, the first word of my talk. On left you have the C API, on right you have the C++ API of random number generator. There is good reason it's like that. Not everybody like that. Even Bjarne himself said that like it's a mistake that it's so complex to start with, to just generate one random generator. But there is good reason why it's like that. Currently, I really like the C++ random generator, because if you do anything serious with random number, you want something that looks like that. You want something where you separate your distribution, your random pseudo-random number generator, or your real random number generator, and you want it to be easy to extend, which is more or less what this API is doing. It has some quirk, but it's a pretty good API, I would say. So if I put myself in the shoes of Bob, I'm a PhD student, I don't know much about C++, I don't know much about the API. I kind of understand the bottom part, because the bottom part is about statistical distribution, right? Like if you're an average student or you went to college, you understand what it is, normal distribution, Bernoulli, uniform distribution, all this stuff. The description of the doc is pretty, okay. The upper part is something else, like the PR energy. If you just read CPP preference, which is this documentation, there is nothing of use about what these random generators are doing. Like you have description of the template, you have bar description of the algorithm which is behind it, but it's not going to give you the properties. And this is one of the first difficulties I do find. If you want more detail about that, but probably most of you knows it, because you are CppNow attendants, let's say, so you are not beginner on that. These are the main algorithms you do find in the C++ random API. So you have Ranux. Ranux is pretty old currently. It has excellent random quality, and it's used also by the CERN simulation software for many, many years. So it's a random generator you can trust currently. However, it's very slow. It's around 8 to 10 times slower than what you would get with Mersenne Twister or with the other one, in the most common form. It has a pretty big period, and I put the age at the end because I want to make people understand that most of these algorithms are currently pretty old. It's from 1994 for the first publication. You have Mersenne Twister, which I will describe more in detail, but Mersenne Twister is a good compromise on everything. It has pretty good random quality, it has pretty good speed, it has a huge period, meaning it does not cycle easily. And it's more recent than the other one. And the two other one are min_std and the Knut. Knut, if you have your example of art of computer programming, you probably have it inside. And min_std is more like let's say, legacy algorithm, which has a pretty bad random quality currently. Out of one number, you can easily predict all the other one. So if you're doing anything in machine learning, scientific, and that, you really want to avoid this. And that bring back, if you put yourself back in Bob's shoes, you want more or less to choose Mersenne Twister for anything scientific. It's good compromise, you're gonna run fast enough, you're gonna get a random quality which is good enough for what you want to do. And this is a good default for the use case, right? If you have any question, don't hesitate to interrupt. One thing I want to point there is currently the default random engine that you have in the standard point to min_std. And I think it's a terrible default, because it literally means that the default option that you propose in your C++ standard is a bad random generator, that's something maybe we should think a little bit about.
So the standard got a default wrong?
No, the standard didn't say anything wrong. The implementation, if you take Clang and GCC, thank you to correct it, most of the implementation default on this random generator. More on Mersenne Twister, so just for a little bit of literature on think on it. It's developed by Makoto Matsumoto, I'm sorry for the pronunciation, and Takuji Nishimaru. It's a pretty old, that comes from this paper if you want to read more about it. And it's a pretty old random generator at the end. But it's still considered nowadays as a gold standard, it's a safe value if you want to use something, and by default you don't know it. And it's widespread in countless number of programming languages, not only in C++. If I would compare Mersenne Twister to something, I would compare it to the Toyota Camry, that's not the most sexy car ever, but that does the job. If you want it, it's gonna bring you far for a very long time. So now let's get back on Bob's shoes. If you're the average PhD student, you don't know much C++, and you try to program your first simulator, or one of your simulators, you will get with something related to this algorithm. So you're gonna define a seed randomly, 42, a very random number, right, like usual. You will instantiate Mersenne Twister. You will do your for loop where you are gonna iterate to whatever data you want to work on. This is very simplified code. You have your distribution that interests you, you generate your random number, and you pass it to whatever kernel of compute that you want to work with, or you're gonna pass directly your random number generator inside it if you generate a stream. Anybody has a criticism for that? Or disagree about something? Does it look good to you?
Seeding.
The seeding is bad, yeah. But I'm gonna come back on that later. So this is the sequential part. The seeding is bad, but we can ignore that for now. Let's put it to the parallel form, and I can swear to you that if you take 90% of the scientific code that you get around, or even most of code using Mersenne Twister, which are parallel, meaning using multi-threading, you will get something like that. So if you look very well, you will not get something like that. Let me reformulate. So if I'm Bob and I'm doing it on the first time, I'm going to try to do something like that, right? I will put a giant mutex more random number generator in my parallel section. This is OpenMP, for the people that don't know it. It means that you are going to execute this for loop in parallel in different threads. That's it. I use OpenMP because at least it fits on the slide. I'm not a big fan of OpenMP. I currently dislike OpenMP, but it makes it fit on the slide. Well, the thing with that is, of course, like everybody knows here that if you put a huge lock around your random generator to guarantee that you have an uniform stream of random number around that, your HPC engineer, when your code run into production, will probably look like that. Like it's not going to be a P. Like your code might be even slower than like if you run it sequential. What you do on this time in 90% of the code that you found is something like that. Like you don't, so I did with thread local variable again to make it fit on the slide, but like you can write it with a double nested loop, one for threading, one for like block decomposition, of course. And it's gonna make it a little bit not using thread local first and more appropriate. So what you will do is you will typically initialize one random generator per thread, right? Can anybody tell me what is wrong about that? So except the seeding. You can go for the seeding, but tell me what's wrong about it. So even if you use seed sec to like bypass this command, it's still wrong. Like you are currently instantiating like a random generator with a seed per thread, and you can still get correlation between them.
They're all generating the same numbers?
No, they are not all generated the same number because you do have one different seed per thread. You have the seed and you are using currently your thread ID as seed initialization. So like you have a correct one random generator initialized per thread. But you are still gonna get correlation for that. Like random generator, especially Mersenne Twister, they guarantee you that inside a stream, you do not get correlation within your number, but between the stream, you can get it. So if you're unlucky, you still get correlation. And currently, you can grant that even on slide of some people in CppCon keynote that do something like that. That's open. It's something you should avoid. What generally you need to do, if you have a question, feel free. What generally you need to do will be at least what Mersenne Twister advises you to do is you need to jump forward. So what you're going to do is you take your huge period, your random generator that are a huge period, and you use the discard function, which means that every thread will have a window of random number, which like you can generate with it. That's more correct, but in my mind, it doesn't make it good, right? Like, does anybody see like everything that can go wrong with that?
Is discard linear?
Yeah, that's one thing. Not every random generator are constant time when you jump forward.
But
So
I don't think the implementations implement the log jumping for some of them.
yeah, exactly. That's one of the problems. The other problem is you have to be very, very careful that your window do not overlap. Because they're like, I'm offsetting of like 32 bits number more or less. So if inside my for loop I have a huge data set, I might currently overlap my window. And then I have problems. Because I will get like correlation between my random stream. It's just not something practical to do. And also, other problem that you do have is Mersenne Twister has a big initialization phase. When you start in Mersenne Twister for the first number, you're going to do the initialization phase. So you're going to do this initialization phase for every of your thread right now. So in terms of time, it's not so much a big deal, but in terms of energy, you're using compute for nothing. So is there any better solution to that? So I have another question for you. Like, is there a category of function where like you can give it a key, you can give it anything, and you get something at the output that looks like noise? Hash is a good answer, but more general? Any cryptographic function, like block cipher. Block cipher is a very good one. If block cipher, any block cipher algorithm that you are using, if you want to do any symmetric type of encryption, like they have this property, right? Like if you encrypt something and you have some statistic properties in like the encrypted version of your data, you have a big problem. That means someone can guess whatever you have on your data. And that's currently, the answer. That's currently what is the concept which is behind counter-based pseudo-random number generator. So like you take a block cipher, you take a key, you take a counter, and you can get random content out of it. And there is something which is very beautiful with that is, you solve a lot of the problem currently. Like first, you don't struggle much about setting up your seed anymore. Your seed is not that much important because your seed is going to be like the key of your algorithm. It's the key of like your block cipher. So like if you have seeds that are literally 1, 2, 3, 4 in different data streams, you're going to be okay because if your block cipher is correct, it's going to be resilient to it. The second thing, which is really, really beautiful, is that your random number generator becomes stateless. And that's a big deal. Because if you take Mersenne Twister just has storage space internally taken 2 kilobytes. If you have like what you get in easily in an HPC system, 1 million or like 100 million stream of random data in parallel because you're working with particular stuff like that, you get problem. Because it take memory. So it's gonna take memory bandwidth and it's gonna. The advantage with when you work with that is you can set your counter arbitrary. Like the only state you do have inside that is your counter literally. So like I can generate something like 100 number, I can switch to something else in my algorithm, I can do something completely different even with some random number. I know that I already generate 100, for instance, random number in my first place because I very likely keep track of something of that inside. You know, I know that I'm in my simulator at my time step number 100. I know like the number of random number that I have done before that. So I can literally recreate my random number stream exactly at the time point where I was, and I don't need to save anything. I don't have these 2 kilobytes of data that are hanging around. If you put back at the code that I did before, you get more or less something like that. It's much cleaner and much shorter. Like you declare your counter-based random generator there. I will explain more or less the detail of the template later on. You set your key, so you can set your key with the seed and you complete it. Like in this case, I'm using an arbitrary block size, and I will explain why I do that. And after you put your counter, and the counter in this case is nothing else than like my position in my dataset modulo the block size. And that has another big advantage is what will be the inconvenience before when you do the discard method? Like, you know, one important thing when you do scientific simulation is you want the thing to be reproducible. And if the number of random streams that I spread depend on the number of core and thread I have, that means that if I take my laptop and I have some scientific result and I put it on your laptop and you have different core number, you're gonna get different results. And that's not great. Like when you do scientific simulation, you want that the guy that reused your software after get exactly the same stuff than you, to show that you didn't fuck up somewhere. If you do that, you don't have the problem. Because then you divide properly your dataset in a given block size, and you have random streams which are per block size on your entire dataset. They do not correlate with any number of threads that you do have. That's currently good. And also you solve all the problems that were reported before of like jump ahead, which is not in linear time, initialization phase, and all of that. And that makes Bob happy currently. Now let's get back to the second part of what I put in the talk. Like faster, is it that faster or not? So there is a publication that has been done like some years ago, in 2011 currently, named Random 123, that's done by the Shaw Institute in New York. That currently gained one of the prizes of the best paper of supercomputing in 2011, if I'm not mistaken. That defined an entire family of counter-based random generator. And how they do that is they more or less took like the most common block cipher that you have around, which I'm gonna describe after. They reduce the number of rounds to keep like the good statistical properties of random number generator without too much complexity because they are faster. That gives something like that. So there is 3 ones that are already described in the publication. There is IRS, which come from the IAS block cipher. There is 3fish that come from 2fish. And there is Philox, which has been done from scratch, and I will come back from that. They all have different nice properties that you can probably guess a little bit out of what I wrote on there. Like IRS is based on AS, meaning like you have in quite a lot of processor dedicated instruction for that. So like you're gonna compute a block when you're running your algorithm directly with hardware instruction. 2fish is currently pretty fast. It's come from Schneider, I think, if I don't say mistake. Schneider, thank you very much. And it's pretty flexible and fast algorithm to start with. So it's not going to be as fast as IRS when you have the instruction, but it's going to be fast on almost, relatively fast on almost every first one. And Philox use only multiplication on modulo, and that can have some nice usage. Like, if you take in terms of performance currently, if you have Mersenne Twister compared to like the three other algorithms that come in the publication, you see that this performance, by the way, comes from the paper. Like, I have my own library implemented of all of that with some code cleanup and stuff. I didn't want to put my bench there. I want to keep the one of the paper because that has been peer reviewed. You can see that IRS currently for the CPU are from 2011 too, so like you get some difference right now. I'm gonna get back on it later. As long as you have like hardware instruction, the one based on IRS is generally faster on CPU. FreeFly is pretty good compromise on every platform, like you on CPU, GPU, or any accelerator, since it's an algorithm which doesn't have branching, is mainly XOR based and can be unrolled entirely, so it has a pretty low memory footprint. It's quite fast. On Philox, in fact, since it's based only with multiplication, you don't have any XOR compared to all the other. It's blazing fast on GPU. The GPU love that. Like GPU love multiplication. They are made for it. And like you more or less destroy everything else in terms of perf on GPU. It's so nice currently that if you are using the CUDA random generator, you have it already inside. Like NVIDIA implemented it for you. Like there is one option where you can select it. Yeah, that's it. And so, other side, like when you're using counter-based random generator, first you avoid most of the problem you do have with Mersenne Twister on classical algorithm. You have something which is stateless and it can be faster. So it's quite nice, right? Yeah, now let's get to the stronger aspect. And I think I'm gonna be clearly in advance on like what was planned, but like that you will have more time for question if you don't. The stronger aspect, so what matters for a random generator is that you have good random quality, right? Like the quality of random generator for people that do not know yet about that, like the reference benchmark about it is test U01, and there is two test suite inside it, which is crush and big crush. Like it's pretty standard stuff. Most random generators tend to pass crush. Most of them have some tests that fail in big crush. Mersenne Twister has some tests that fail in big crush currently. So Mersenne Twister random quality on some corner case is less random than what you get for the three over one. Because the three over one, how they did random 1, 2, 3 is very simple. Like they took the entire block cipher and they reduced the number of rounds up to the time that it's not passing anymore the big crush. And when it's past the big crush, they just increase one more and they keep that and they call it like a day. That's what they did. And that worked very well currently. And that's it. So like you get all the advantages that I said before. It's faster, it's easier to use, it's like more compact in memory, and it's currently better quality. Yeah, my conclusion on that is like random is really a nice piece of code, and it's good to get that in the STL. Like it's really well job. Like it's good that C++ even bring that, and it's a huge improvement compared to what C was having. But it aged, of course. The default rule should probably be a little bit reviewed, but like pointed, it's not the problem of the standard, it's probably more the problem of the compiler implementer. It can be hard to use, right, but that's a property of the random generator itself. It's not so much a property of the API. I found the API currently being very well designed. Counter-based random generator tend to be better algorithms for many core because like you have like smaller memory footprint, and it's also much easier to derivate your random number. What you get generally at big application at scale is you start to get a tree of random generator. Like you have some stream, after you derivate multiple stream in a corner of your algorithm, and after like you're gonna get some other function where you derivate again that, because you want that if you change one part of your program currently, it doesn't affect all your random stream and the other part of the program change. Like that, you minimize like the impact that it has on your simulation. Counter-based allow you to do that very easily because you just change your seed and you extend your seed depending of like which part of your algorithm and your program you touch, and you solve all these problems. And so, yeah, the random quality tend to be a little bit higher. So like my point for this talk was mainly like, I think there is room to put this kind of counter-based random generator on also the other ones that are more modern, like there is XOR Shift, XOR WO nowadays, probably in the STL. It can maybe be a candidate this, I evaluate after the presentation of like the last day. If someone is motivated to make it a B-man project. I mean, I have an implementation currently of all of that, which is clean. I don't put it public because and I didn't place my talk on it because it's from 2014, so it's still in C++14. Probably need a little bit of concept on modern stuff inside to make it look better, but it's working. You can also, like if someone wants to do some work on that, you can also base it on the implementation of the original paper. Well, be aware that the paper has been done in 2011 and it was targeting CUDA. And at that time, the generic programming of CUDA compiler was not that great. So like it's a preprocessor party. So you might want to get on something else. That's it. Yeah. If you have questions, I'm probably really in advance, but feel free. Yeah. Yeah, feel free.
Do the crypto generators have sublinear discard algorithms?
You mean when you set the counter, right?
Yeah, if you were to call discard on the CBRNG.
You don't call discard on the CBRNG. In fact, you just set the counter to whatever value, right? So you are not touching the internal state. You are just touching the counterpart of when you like your block cipher. So it's constant time, always. It's always constant time.
So advancing it is constant time.
Always, yeah.
So I think it's clear that there are advantages to these generators compared to what exists in the standard library. Can you elaborate more on how it compares to other exciting PRNGs that are being proposed to add to the standard library?
Sure. I don't know which one are proposed to the standard library right now. Like, sorry for that.
Third-party libraries.
One of the main one is Xorchief and Xorwo. They are already better than Mersenne Twister because like the internal state is much smaller and the random quality tend to be better. But they still have a state, right? What I really do like with the counter-based one is this lack of state and the fact that you can easily jump forward at any point in your stream, and that they're also very resistant to whatever seed you put on them, make them very useful for scientific simulation, because this is something you really don't want to fail or miss or do a mistake there. Because, I mean, for the little anecdote, I worked in a project before where like they got one of the paper on the front page of Nature, and they realized after the publication that the random generator was wrong in this publication. And that's something you really don't want. That looks like, for a scientist, it looks terrible. So if you can at least, if you could protect a little bit by default that, I found it's a nice property. Yeah, feel free.
Yes, since I think the last question was about random number generators being standardized. Library Evolution Working Group forwarded Phylox in Tokyo.
Which makes a lot of sense for GPU. I guess NVIDIA is pushing for that, or I would say. So Phylox will be nice, but if you do Phylox, you have the structure to do counter-based random generator, because how it is done right now in the CUDA implementation, if I'm not mistaken, is they use it like a classical random generator. So like they hide the counter internally, and the counter is automatically increased when you generate a new random. If you change a little bit the API and you allow to set this counter, you can do very fancy stuff. Like your API is much better, and you can do what I was saying before about the tree of stream of random generation. So that's good that they add Phylox, but if they add the API to add Phylox, they should also add, I think, FreeFly on Ars, because these ones are very good for other platforms but GPU. I know that NVIDIA care probably about the GPU more than the other one, but if you do one, at least do the free. Like, it's easy to do. Yeah.
The usual, one of the usual criticisms of C++ randomness is the distributions are portable. Is that a problem for scientific?
It is, yeah, because it's come from what I was saying before I have my simulation done on my laptop. I want to transmit it to your laptop. You might be a different compiler, but if you have like Intel processor, there is no reason, even if you have a different number of core, that you don't have exactly the same result binary-wise. And due to this kind of implementation subtlety, you don't have that. I think also one thing that would be nice to add is to add a set of random generators which are specified entirely, and whatever platform they get the same number, at least for the test. If the distribution could be reworked a bit, that would be nice. But no, that is more. I mean, it's already inside the STL, and changing something inside the STL is always complicated. Yeah.
So with the stateful generators, we were doing fun things with thread IDs and discards to make sure that their randomness ranges don't overlap to produce a statistical correlation and such. With the stateless generators, like these cryptographic block,
Yep.
sorry, the words, you have the seed and you have the counter.
Yep.
Do you have guidance on like which to use in order to accomplish that? Like
So-
in your example, we used like a
The seed. The seed.
modulus.
Generally, you use the seed more, and you keep the counter to like, if you're interested in having one stream, like if you take a typical example, like if you have a neuron simulator, you have like all your neurons and they are spiking sometimes. You want to have one stream per neuron. You might have billion of neurons, but you want to have one stream per neuron. Like that, like you can literally, even if you want to debug your software, you can pause some and you don't influence it like the other one. So what you do is you derivate your seed for every neuron. And the counter rest, evolve still incrementally. That's how you do. How you construct the seed. The seed for this, if I'm not saying mistake, are 128 bits. So like you have several ways of you can generate them like cleanly and uniquely in a program. I mean, 128 bits is already a lot of entropy. Like it's a UID. So, yeah. That's okay. That answers your question. Anything else?
More
Yep.
general question. It's been a very long time since I've done scientific computing. How big of an impact does that much of a boost in random performance have on either the quality, because they can do more, or how big of a deal is this?
The quality for some type of simulation can be very important. For some other, it does not really matter. But some type of simulation, it can literally fake your result. The performance is highly dependent on what you do. Like for neuron simulation, it's currently not that much. If you do things like Monte Carlo or this kind of stuff, it can be like a big part of your compute currently. So it varies on what you do. It can be a lot. And especially like the old generation of random number, they don't play well with GPU. And nowadays, like if you want to do something fast, you do it on GPU. So I think that's why NVIDIA is doing what they are doing right now, and they're right.
Thank you.
Yep.
So one of the problems with the Mersenne Twister stuff is that the necessary entropy for seed. What requirements are needed for these generators?
Let's come back to what I was saying. I'm not a mathematician or a cryptographer, so I don't want to tell you mistake. But they tend to be much more resilient because like they are based on cryptographic function, and cryptographic function by nature tend to be resilient to whatever key you give to them. Like they don't put very strong requirement on the key. If you want to know the detail, I advise you to read the paper about random 1 to 3. But in my experience, what we are doing in a scientific simulator, just doing basic construction of the key by fulfilling 128-bit, composing, several U32-bit or U8 integer, just putting them in a vector and transferring it like that was enough to get a good random quality. We didn't detect anything bad.
Yeah. Okay. So my understanding is that the cryptographic algorithms have been weakened in order to make them faster for random number generation.
Exactly.
Right?
Exactly. They have been. They reduce the number of rounds. But even reducing the number of rounds, cryptographic algorithms are made like crazily defensive. Like if they arrive to break 1 or 2 rounds, generally it's already a big deal. So yeah. One more question here. No? Okay.
I'll ask one. If you look, a lot of the newer CPUs have random number generator instructions. Are they any good?
It's first, sometimes no,
Yeah.
but they are not really relevant for scientific simulation because you want them to be reproducible, right? Like whatever you have on CPU is true random generator,
Yeah.
tend to be, which we don't care about that. Like,
For cryptographic purposes, maybe. I'm wondering how they play.
So the cryptographic functions are very different of what generally the CPU instruction give you for random number. Like cryptographic function in case of AES, they're just gonna execute 1 round. Like if you do it software or hardware, you can verify that the output you have is currently the same. Like, whatever the implementer of the CPU is doing is checkable. It's always gonna be the same stuff. When you have instruction to give you just random number, you have to trust that whatever they give you is good. At least in my experience and in what I have done, we never use that because you want that when you run your simulation again, you're able to get back your result. Like You don't do that with this kind of thing. So you can use it to get your seed if you want some time, but I would consider that done if there is no other question. And no? Okay, finished.